Hello, everyone. Can you hear me? All right. Thank you. It's wonderful to see you all here for our Monday speaker. We're always lucky when it's a resident giving the talk. And I want to thank you, Hartmut Peters, so much for preparing this for us, for telling us about your life as an oceanographer. One request is that you hold questions mostly to the end so that everybody can hear the questions when we bring the microphone around. Let's give a warm welcome to Hartmut Peters.
Well, thank you very much, and good afternoon, everybody. Many of you, or most of you, know that I'm a retired physical oceanographer. After Lynn and I had moved to the Hearthstone, I was asked more than once what physical oceanography is. So here's some fragment of an answer. First of all, to avoid misperceptions, the emphasis here is on physical. The fields of physical, biological, chemical, and geological oceanography. I'm not talking about the non-physical stuff. No coral reefs, no cute seals, no singing whales in this talk. I would like to start out acknowledging the debt I owe to my teachers as well to the many colleagues, technicians, and students I have worked with over my professional career. We were all working in a highly competitive environment, competing for research money nationwide. And of course, we all peer-reviewed each other. But we also get together to cook up joint research program. And by and large, it was pretty collegial. What you see on the screen here is the output of a numerical circulation model, a computer model of the currents in the North Atlantic. You see the turbulent ocean. It's pretty realistic. The color you see here indicates the sea surface temperature. So there are going to be three parts to my talk. The first part is indicated to provide a flavor of linking theory and observations to each other in a useful way. This part is related to some of the teaching of graduate classes that I did over the years. Part two illustrates my own research work, and part three is more on the personal and entertaining side. This photo was taken on the equator, smack in the middle of the Pacific Ocean, on the good old Thomas G. Thompson. She is not around here anymore. Okay, part one, linking observations to theory. So this is not physical oceanography 101. It's not a systematic survey. I'm just focusing on one specific aspect of ocean dynamics, and that's the effect of the rotation of our planet on the ocean circulation and how you can take advantage of that. The photo shows sunrise over the Seychelles in the Indian Ocean, taken during one of my research cruises. You will see more neat pictures later. Okay, this is also a depiction of the surface currents of the ocean. But this is not the output of a computer model. These are the real currents at a specific place and time. The time is indicated at the bottom of the panel here. And this animation here was derived from satellite altimeter measurements of the sea surface heights from satellites. And I will try to explain how this works, how you can come up with this kind of information, which, by the way, is quite useful. I'll come back to the features you see here in a little bit. So first of all, we have to do more of the hard part. So what is physical oceanography all about? It talks about ocean currents, waves, temperature, salinity, and more. It tackles how the ocean circulation is driven by the sun and the winds, and it talks about air-sea interaction, how the atmosphere and the ocean are coupled. I want to point out here that there's a close relationship between meteorology and physical oceanography. At their core, the dynamics of the atmosphere and the ocean are the same. So why bother? We need to understand the physical processes in the oceans, to understand climate and climate change, to understand the chemistry of the ocean, and to understand life in the ocean. Marine biologists and marine chemists need a solid understanding of the physical processes in the ocean. At Stony Brook University, I taught the physical part of a core curriculum of physical, chemical, biological, and geological oceanography. These were 100 and 200 level graduate classes. Why bother part 2? Oceanographers put out all kinds of useful things. They make climate forecasts together with meteorologists, biologists, chemists, and possibly even economists. Oceanographers make ocean forecasts similar to a weather forecast. And a core part of that is predicting the currents. And these kind of predictions are used by navies, the maritime industry, and serious yachts people. I don't know if Jim Killingsworth is here today. He would probably appreciate such forecasts. Oceanographers forecast El Nino, which is a serious short-term climate fluctuations that can be very dramatic in the tropics, but affects us here in the Pacific Northwest too. Oceanographers forecast tsunamis after big earthquakes. And they do routine forecasts of tides. They do storm surges and hurricanes together with meteorologists. Oh, there's Jim. He just came in. Okay. How important is the world ocean? Oceans cover 70% of the ocean, of the Earth's surface. But more important is that the world ocean has over 1,000 times the heat capacity of the atmosphere. That is to say, the ocean contains almost all the thermal energy of the atmosphere-ocean system. So that implies when you look at climate and climate modeling, that in climate models, you especially have to get the ocean part right. And the further you project your climate model out in time, the more important the ocean becomes. The scientific basis of oceanography is essentially mechanics applied to a continuous medium. So it's courtesy of Isaac Newton. So it's formulated as conservation principles of mass, momentum, and energy, and they're expressed in mathematical equations of how the conserved variables changes, so it's not static at all. I won't bother you with these equations. I just mentioned this here to unequivocally state that physical oceanography has a sound scientific basis. So what I want to focus on here is that we are living on a rotating planet. The rotation causes some complications. And when you write out these equations of the conservation principles in a rotating coordinate system attached to the Earth, you get some extra terms, one of which is the Coriolis force. It's kind of a strange thing. It's been referred to as a pseudo-force, but it's really very real. What it does is that the Coriolis force pushes moving objects to the right on the northern hemisphere, to left on the southern hemisphere. And what it means is that ocean currents and winds are fundamentally affected by our planet's rotation. So here's an example. These are measurements which are very old, but still very useful. What you see here is the trajectory of a surface buoy observed in the Baltic Sea long time ago, starts out here, and you see that the buoy goes in clockwise circles, which become smaller and smaller. The scenario here is that the wind had been blowing over the ocean for some time and then suddenly stopped. But the water on the ocean surface conserves its momentum. It keeps going. So because there's rotation and because there's the Coriolis force, it goes in these circles. You can see this kind of thing oftentimes. And on the southern hemisphere, the circles would be counterclockwise. Now, next, we're going to look at what the Coriolis force does to major ocean currents like the Gulf Stream. I don't want to discriminate here, so you can exchange the Gulf Stream with the Kuroshio, but I'll refer to the Gulf Stream. So in my simplified sketch here, North America is at the left. We are looking into the plain, and the Gulf Stream is flowing into the plain, as indicated here. The open Atlantic is on the right. And what's important is that the sea surface is not flat. Across the width of the Gulf Stream, which is 50 to 100 miles, the sea surface drops by 3 or 4 feet. So that's the factor we want to look at here. Okay, so the water in the Gulf Stream is moving. The Coriolis force pushes it to the right. You can think of the water being piled up on the right here. So there's more water on the right than on the left. So there's a pressure gradient force. Water tends to, or tries to move from higher pressure to lower pressure. But it's not so simple on a rotating planet because the pressure gradient force is balanced by the Coriolis force. Okay, and so the current flows at right angles to either the Coriolis force or the pressure gradient force. By the way, the balance between these two forces is not exact. And in terms of dynamics, the deviation from this balance is actually what's interesting. But that's beyond what I want to talk about here. So here's the recipe we need for what I promised you. It's how to exploit the balance between the Coriolis force and the pressure gradient force. So there are 4 parts to the recipe. In ocean currents, the pressure gradient force and the Coriolis force balance each other. The current flow is at right angle to either one of those. The current speed is proportional to the pressure gradient force, and the pressure gradient force is proportional to the slope of the currents, to the slope of the sea surface, excuse me. So here's our satellite. It measures the distance between itself and the sea surface. And the guys who run these satellites know exactly where the satellite is. And the satellite can actually resolve the topography of the sea surface to an inch or so. So the drop here is 3 to 4 feet. So this is easily measurable. So then you can generate a map of the sea surface topography, convert the map to a current map, and then you get this picture here. This is a product called Oscar. It's put out to this very day by Earth and Space Research here in Seattle. That was incidentally my last employer, but I was not involved in this Oscar project. So let me point out a few interesting things here. So here's our Gulf Stream, and you can see it has nice meanders, and sometimes the meanders pinch off and form these rings. There's a loop current in the Gulf of Mexico, and that pinches off at times too. Here's the Kuroshio, so that's the counterpart to the Gulf Stream. Let me see, Brazil current, Malvinas current, Algulhas current, and then there's the circumpolar current going all the way around here. And you also see some neat things happening in the equatorial belt here. The horizontal component of the Coriolis force is 0 at the equator. So the dynamics of the ocean currents are different around there. And there are all kinds of phenomena going on that I can't get into here. Okay. So that was the end of part 1. So we're getting to part 2, a glimpse into my own research work. For a background, I have to tell you that I got my education up to a PhD in Germany. I got my PhD from Kiel University, and I worked there as a researcher for a while. I went to the Applied Physics Lab of the University of Washington in 1984 as a postdoctoral scholar. And that's where I really learned to conduct my own independent research. I did so first as assistant professor at Stony Brook University on Long Island. I didn't get tenure there, so I moved on to the University of Miami as a research associate professor. That was sort of falling up the stairs because the Rosenstiel School of Marine and Atmospheric Science at the University of Miami certainly at that point was a much better school than Stony Brook. I would like to mention here, just for curiosity, that I have never had a permanent position in my entire life. My employment was always either time dependent in the first place, or I had to bring in my own salary via research grants. Okay, what you see here is yours truly operating a winch on the Hudson River alongside Manhattan. So my first project was turbulent mixing in the Hudson River estuary, which could be dubbed urban oceanography. So this was my first independent research project. I designed the experiment, had the instrumentation designed, wrote a grant proposal for the instrumentation, got it designed and built, wrote a grant proposal for the experiment itself, got it all funded by the National Science Foundation, carried out the observations, analyzed them, wrote up the results, got them published in peer-reviewed journals. Of course, I had a lot of help from technicians and students along the way. It was a lot of hard work and quite exciting. So what you see here left is us working in the Hudson River, left is Manhattan. On the right is our research boat and the Twin Towers of the World Trade Center intact. Okay, let me describe the experiment a little bit here. Here's the geographical setting. This is just a satellite image. This is the Hudson River here. This is New York City. Here's Manhattan. Long Island Sound and New York Bight. So this is an estuary. So there is seawater intruding up the river and fresh water coming down the river, and there's mixing in between the two, which was the objective of my research. And when you look at the vertical versus distance along the river, there's the heavier and saltier seawater here and the river, fresh river water. So this is the relative circulation of them. And the whole system is shoved back and forth by the tides. The tidal flow is much more stronger than this opposing estuarine flow. And there's the mixing in between here indicated by this arrow. So this mixing between the salty water and the fresh water is an essential component of the estuarine circulation. It's important not only for the physical dynamics, but for the biology and the environment. For example, there still is a lot of pollution in the Hudson River, not unlike the Duwamish. For example, there's still a pound or two of PCB leaking out of an ancient GE plant. So you want to know where that stuff goes. And you have to account for the mixing between the layers. When I did this in the early 1990s, there was limited understanding of the mixing itself and very few measurements. It's pretty difficult to measure. So the microsector measurements, which I will explain in a minute, were the remedy. The plan was to quantitatively observe this mixing related to the flow conditions, the tides, and the river flow, etc., and improve the representation of this turbulent mixing in numerical circulation models. So to that end, we need measurements of current, temperature, and salinity, plus measurements of small-scale fluctuations of velocity, temperature, and salinity. That's usually referred to, the kind of measurements I took are usually referred to as microstructure measurements. Measuring the currents is easy. You just buy yourself a gizmo that is an acoustic Doppler current profiler and put it in the bottom of the ship, configure it, turn it on, have it record the data, and do something else. Okay, here's how it works. So there are acoustic transducers in the bottom of the ship, and they send acoustic pulses down towards depth on slanting beams. And the sound is backscattered both from within the water column and from the bottom. And the frequency of the backscattered sound is slightly altered because of the velocity along the beams. That's the Doppler shift of the frequency, which is exploited. So you look at these signals, and you first get the velocity along the beams, and then you apply some geometry, and you get the horizontal velocity. And then you combine the measurements from the water column with the measurements from the bottom to get the current velocity relative to Earth. Okay. So here's the microstructure profiler, which was designed and built for me. It was one of a kind. It was pretty darn cantankerous. We called it, well, I called it the shallow water microstructure profiler, or SWAMP. So the instrument is here, is roughly 5 feet long. We operated in a quasi-freefall mode. So it was just falling down at a good rate of 3+ feet a second. And it was connected to the ship with the cable, which was just loosely floating around. And we used the cable to haul it back to the ship. And the cable was the data link, of course. So here, in this part here, were the sensors for electrical conductivity and temperature and pressure, which converts to depth, temperature, and salinity. So that's the conventional part. The sensors were built by Siebert Instruments, by the way, the professional home of our own Julia Robinson. Okay, so the part that measured turbulence was located down here. A fast thermistor measuring very small fluctuations of salinity. A small connectivity sensor with just higher resolution of salinity, and a thing called a shear probe, which you can look at after the talk, which measures velocity fluctuations. So there's also a probe guard, and we let this thing bounce off the bottom after we gain some confidence in it. Left is the beast on the workbench, worked on by expert technician Robert Jones of the University of Miami. And at right is deploying the swamp in a good wintertime gale in the Adriatic Sea. But let's get to the Hudson River. Here's just one example of these measurements. This is one single profile. So let's start on the left here. 0 is the floor of the river. The dashed line here is the surface of the river, so it's not quite 14 meters deep. The green curve is the velocity. It's negative, so it's flowing out. This was taken during ebb. And it's a pretty healthy flow, 4.5 miles an hour. Velocity, the speed increases towards the top, so that's the combination of the river outflow and the ebb flow. The red curve is the salinity from that microscale conductivity sensor. And you see all these wiggles in here. That is the turbulence. So salty water is heavier than less salty water. So you can see here that there are instances of more salty water over less salty water. That means heavier water over lighter water. So the turbulent worlds work on the water column against gravity. You can see that in a more formal way on the right-hand side here. Gives you the structure of these worlds or eddies. Now, in the middle is the turbulent dissipation rate, epsilon, which is a curious beast, which I don't really want to get into. Just believe me that it's a key quantity to quantify the intensity of the turbulence. Okay, there were a total of, let me see, six short cruises from 94, 95, and in 2001. And in all of them together, we took over 6,000 microstructure drops along the Hudson River. The results of all this work became useful not only in highlighting the local conditions, but more importantly, how to present turbulent mixing in numerical circulation models. So, end of part 2. Part 3 is the entertaining part, being a seagoing oceanographer. Okay, this is an old photograph from 1970. What you see is the little hamlet of Tasiilaq in East Greenland. Anchored in the bay is the venerable steamship Anton Dorn, which I was on. And you see some icebergs and ice flows in the bay and glaciated mountains. This was my first cruise as an undergraduate student. We went ashore here for a couple hours. The Anton Dorn was not really a research vessel. It was a research support and survey vessel. And she carried a doctor and a hospital. Here's some of us mingling with the locals at the dock. And believe it or not, there even was a detour in that little village. This is leaving the village and going out into the East Greenland current, which is full of ice. It flows southward along the coast. Big ice flows, big icebergs. And for the birders amongst here, I want to mention that I saw a geofalcon perched on one of the ice flows. Big iceberg. My first cruise was perfectly miserable. It was windy most of the time. I was seasick most of the time. There were only 2 physical oceanographers on board, myself included. My boss was a failed student and a miserable alcoholic. The guy drank whiskey out of a beer glass at night while we were taking water samples. Meanwhile, the fisheries biologists were soundly snoring away. My first real research cruise was in 1972 on the German vessel Meteor. The study area was the upwelling area of Northwest Africa, of Mauritania and Senegal. California, Peru, and Namibia have similar upwelling areas. So the upwelling brings cold and nutrient-rich water from depth up to the surface and feeds very rich marine life. So this is some old 8mm footage of leaving the port of Hamburg in the wintertime. There's ice in the river. And we skip the way along. This is a catamaran being towed on the surface to collect plankton that lives near the surface. You can see the net coming up. This is physical stuff now, a water sampler being attached to a steel wire. And you put a whole stack of these on the wire, and the messenger weights in between, which trigger all this. This is more modern, an electronic probe measuring effectively depth, temperature, and salinity. At that time, it was powered, let me pause this, powered by vacuum tubes, and probably burned a kilowatt underwater. It was fed by about 500 volts DC. Of course, it's loads of fun to run around on the open ocean in zodiacs. And I assure you, this was a perfectly fine day. There was just a little bit of significant swell. There were two ships in this experiment, and we went back and forth in between them. Here we go. Okay, that's the meter I was on.
Did you get over being seasick ever?
Yes, in my 50s. Yeah, miraculously, it disappeared. It's not so uncommon for oceanographers to get seasick. Oh, there. Of course, there were opportunities for shore excursions. This is a village in a mangrove-ringed estuary south of Dakar, the capital of Senegal. And this is a photo of the island of Gorée, which is just offshore of Dakar. This island holds the infamous door of no return. So that's the door through which countless enslaved persons were forced on their way to the Americas. Okay, here's a map of some of the places around the globe where I've poked around as an oceanographer. Red are cruises in which I was intimately involved in the scientific research. Blue are cruises as student or worker bee. Purple or pink cruises where I had substantial input but didn't participate in any publications. And white are places of interest. It's been an interesting professional life. So here are just some highlights from what I've done. This is the GATE experiment of 1974. That was mainly atmospheric, but there was an oceanographic component. It was started by the Global Atmospheric Research Program. What you see here is the US Coast Guard cutter Dallas, number 716. The tethered balloon is used to fly meteorological instruments. Here's the Russian counterpart, the Professor Wiese. You see, it's built like a passenger ship, and it was actually very comfortable inside. We visited this ship too. But it had to be comfortable because the poor Russian chaps had to go to sea for 9 months at a time. This is a different cruise. And as usual on German ships, there were all kinds of different disciplines represented amongst the scientific crew. And when you have a bunch of biologists around, you might see interesting creatures. So this is looking through the microscope. And I don't know what this is. Unfortunately, Jim Kanagi isn't here. He could probably tell us. But this creature is very small, as is this. I mean, this is a little bit over 2 inches long, obviously a predatory fish. And this is a very, very cute baby squid. Yes, yes. Okay. So as I mentioned, in 1984, I joined the Applied Physics Lab here in Seattle. And my first cruise on an American ship, the Thompson, was cut short because I broke my elbow at sea. Was put ashore in the middle of the night in Hilo, Hawaii. And jumping into the bobbing launch wasn't half bad, but when I got to the emergency room and they started taking x-rays and moving my arm this way and that way is pretty awful. So left is one of the staterooms. And I must say that the Russians had a lot more comfort than this. It's fire resistant though, so meets Navy standards. In 1987, I made it through a whole cruise to the equator, to the tropical equator in the Pacific. And the photo on the right is from that. That's a big freefall profiler, which went down to like 1,000 meters and came back up on its own, hopefully. You can still see it at the Applied Physics Lab. So in 2003, I joined an Office of Naval Research funded experiment in the wintertime Adriatic Sea, was appropriately called Dolce Vita. I don't recall what the acronym stands for. We were looking at what happens in the ocean under the strong bora winds that blow through the gaps in the Croatian mountains. So these winds are very cold. The sea is relatively warm. The wind is strong, 50 plus miles per hour. So you see that I was dressed up pretty heavily. On the right is an instrument that we deposited on the bottom of the sea for a while and then recovered. My last experiment at sea was in 2009, the Mediterranean Internal Wave Experiment, which looked at the outflow of salty water from the Mediterranean into the depth of the Atlantic Ocean, a process that's climate relevant. So left is myself at work at sea, and right you see the fancy opera house of Valencia. We started out the work in Barcelona to get the ship ready. So that's not too far from Valencia, and I visited a high school buddy of mine there whom I had not seen since 1966. The cruise itself began and ended in Cadiz on the Atlantic side of Spain. And I took the opportunity to take the train to Cordoba and visit the Great Mosque. So on the left is a small part of the vast interior of the mosque, and on the right is the prayer niche, the mihrab. This mosque was built from the 8th through the 9th century and is a World Heritage Site. Cordoba has a very rich history. In the days of the caliphs, the religious climate was rather tolerant, as long as you paid your taxes. And back then, Cordoba had a significant Jewish community. Left is a monument to Moses ben Maimon, known in Spanish as Maimonides. He was a prominent 12th century rabbi, Torah scholar, and philosopher. On the right is what is left of the ancient synagogue of Cordoba. It's the women's gallery. Okay, we are getting closer to the end now. What you see here, obviously, is a troublesome part of our planet, okay? So in 2001, we had 2 cruises that studied the outflow of the salty and heavy water from the Red Sea, here. through the strait of Bab el-Mandeb, the Gate of Tears, into the Gulf of Aden, and then into the depths of the Indian Ocean. I should mention that there's a similar process going on in the Strait of Hormuz. So the two cruises were a joint project of Woods Hole Oceanographic Institution and the University of Miami. We were on two different ships, Woods Hole's NOR and Columbia University's Maurice Ewing. Okay. So here's just one quick snap of the observations we did. The whole experiment was pretty darn cool. I can't get into all of that. But here's the outflow of this salty water. This is the salinity. And you can see that it's quite salty here. Standard ocean salinity is 35. This was over 39.5. And at right is the velocity of this flow down the slope here. The water goes down to a depth of about 800 meters. This is my colleague and co-PI, Dr. Amy Bauer. She was the chief scientist on the second of the Red Sox cruises. She's legally blind, yet going strong to this very day. You see that she used enlargement software on her computer. Woods Hole Oceanographic paid her husband to come along as a personal assistant, a marvelous example of accessibility and inclusion. When you look at the web pages of Amy, she lists not only her human partners in her team, but also her current and previous seeing eye dogs. I would like to mention here just briefly that women have been doing quite well in physical oceanography and marine biology for quite some time. Okay, the first of the Red Sox cruises ended on the Seychelles. The Seychelles are at 4 degrees south in the Western Indian Ocean, and it's really hot and muggy, but this is an absolutely gorgeous and really safe place. So I took a day trip to a little island called La Digue, which surely has the most beautiful beach on this planet. It's called L'Anse d'Argent, Silver Spring Bay. I mean, just look at it. Okay, here comes trouble. This is yours truly in my stateroom on the Maurice Ewing. And one day when I was off, I was looking out of the window and I saw something that I did not like one bit. There was a speedboat out there with guys armed with an RPG and assault rifles. Okay, so that was the RPG, which fortunately was a dud, and then they started shooting their assault rifles. This video was taken by a graduate student who was probably very bright, but not endowed with a whole lot of common sense. He had explicit instructions to stay out of sight and under deck. You notice that he had to duck twice, once when the pirate dudes fired their RPG and once when they started shooting their rifles. I want you to note the date. This was August 31st, 2001. Now, we were very fortunate in that apparently we were accosted by the least competent pirate, at least in the Indian Ocean. They never tried to board the ship. If they had tried, they would have had absolutely no problem taking the ship over. Okay, so I'm not telling you tall tales here. You can convince yourself that it's all true. Here's the New York Times International. Pirate militias from Somalia spill into the Gulf of Aden. Here's Nature, one of the two top professional science Germans. Pirates attacked research ship off Somalia. So that's the Maurice Ewing here. Well, that wasn't the end of our adventure. Then came 9/11/2001. We were a day's steam east of Djibouti where our cruise was to end. The mood on board had been very jittery anyhow because of the pirate attack. And when the terrorists attacked various places in the US, the crew of the Ewing was pretty much petrified. They didn't even dare dock in Djibouti, even though the place was pretty safe because of the French military base. They anchored offshore, and Amy, the chief scientist, had to convince the captain to get us a boat to go ashore and go home. We boarded a flight to Paris via Jeddah, Saudi Arabia, home of the 9/11 terrorists. I stayed in Paris for a day and a half and was on one of the first flights back to the US across the Atlantic. Being greeted by the immigration officer with "Welcome home" felt mighty good. Thank you for listening to my yarn.
If there are questions, please raise your hand.
Back to the currents that you were showing, the way back, the what is it? The CO something. Is that stationary, always in the same place? I mean, you showed the Gulf current, and then the other one.
This sketch, not sure what you're referring to.
The current.
Sorry. I have to turn the slideshow back on. Come on. Oh, there we go.
Well, you showed the satellite picture of the currents. That's what I was wondering. So is the Coriolis force always in the same place?
No, it's a force that acts on all the movement in the ocean and in the atmosphere too.
Oh,
so
okay.
No, everything you see here is affected by it.
Okay, I thought you said the one on the top right was.
No.
Okay, sorry. What made you interested in oceanography?
Well, all my male forebears were merchant marine officers, and there's many a colorful story to tell about that. So originally I was interested in chemistry, but then the sea was calling.
Here's one. I just wanted to know, I mean, this is all on the east coast. So all of that, the currents there. So what's happening?
Would you mind saying that to me?
Oh, what's happening on the West Coast? We only see all of that is on the East Coasts. All over. I mean, all over the world, it's only showing the eastern parts. Then it's blank in the western parts. Is there no movement there, or?
There is. It's just very much slower.
Oh,
and
okay.
What you see here is referred to as westward intensification. So that's a more complicated aspect of being on a rotating planet.
If we went the other way, it'd be different.
What are the effects that you see from climate change in the work that you've done? What's the effect of climate change on the work that you have done?
Well, the work I did on those currents going down into the depth, that is climate related. And it's part of the climate process that is very difficult to handle in climate models. I have worked together with proper climate modelers.
Maybe I missed this, but why were you being attacked by a pirate ship?
Well, that's a good question. I mean, the pirates were quite active at the time. And when we were out there were boats going back and forth across the Gulf of Aden all the time at night. And they were probably not doing legitimate things.
Hartmut, thank you so much for talking to us today. We
Well,
really
thank you for
appreciate it.
listening.